So let's just quickly go over like how you would prove like the divisibility rule for 9, for example. Like all of the other divisibility rules can be proven in a very similar way. So let's say you have like any number, right? If you have the number like 4, 5, 1, 7, 2 or something, all right, let's make it a smaller number. Like if we have like 451, for example, right? We know that we can always write it in terms of like the powers of 10, kind of, right? So 451 can be written as like 4 times 10 to the power of 2 plus 5 times 10 to the power of 1 plus 1 times 10 to the power of 0, right? So like in general, a bigger number, maybe like 1, 2, 7, 9, 5, 8 or something, you can write this as 1 times 10 to the 5 plus 2 times 10 to the 4 plus 7 times 10 to the 3 plus 9 times 10 to the 2 plus 5 times 10 to the 1 plus 8 times 10 to the 0, right? So in general, for any number, you can always write it as like the sum of powers of 10. So like 1, 2, 7, 9, 5, 8, you can write it as like this. So in general, if you were to have like some number, right? If you had like the number, instead of like, actual digits, let's use variables. So let's say you had like this number, like an minus 1, an minus 2, dot, 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 a1, a0, where like each of these like variables kind of represents a digit. So like you can kind of, so you can kind of think of like this as like a0, this is a1, this is a2, this is a3, this is a4, this is a5. So except in this case, we're doing like a general case of like an an minus 1, an minus 2, all the way down to a1, a0. So if we were to like use the same strategy and write it in terms of like the sum of the powers of 10, we can write this as like an times 10 to the power of n plus an minus 1 times 10 to the n minus 1 plus an minus 2 times 10 to the n minus 2, and then plus dot, 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 plus all the way down to like a2 times 10 to the 2 plus a1 times 10 to the 1 plus a0 times 10 to the 0. So we kind of just like extended this logic from above. Like we can write any number as the sum of powers of 10. And then we kind of extended that logic to a general number here. And we just wrote it in terms of powers of 10. So now like is where like we can kind of use modular arithmetic. So we know like from modular arithmetic stuff, we know that like 10, we know that like 10 is congruent to 1 mod 9. Right, so 10 is congruent to 1 mod 9 because like 10 and 1 both leave a remainder when divided by 9. So the idea is if I were to like kind of like use that fact here, if 10 is congruent to 1 mod 9, I can kind of like replace every 10 I have with a 1 because of modular arithmetic properties. So like I could say that this is congruent to an times 1 to the n plus an minus 1 times 1 to the n minus 1 plus an minus 2 times 1 to the n minus 2. And then you can repeat this all the way down to a2 times 1 to the 2, a1 times 1 to the 1 plus a0 times 1 to the 0. And you can just like kind of remove the exponents because 1 to any power is just 1. So this is congruent to an plus an minus 1 plus an minus 2 plus dot, 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 plus a2 plus a1 plus a0 mod 9. So, and this kind of like finishes the proof because we see that like this original number here, like an minus 1 all the way down to a1, a0, we see that's congruent to just the sum of the digits. And this number here is like the sum of the digits of the original number, modulo 9. So that kind of like explains why when we want to determine whether or not a number is divisible by 9, we can just kind of take the sum of the digits and take that modulo 9 instead and see if that works out.